All right, so here we go. I heard the, oh, here it is, the last one. So I don't have the problem set right in front of me. Yeah. Alright, so here we go, guys. Hydroperoxide decomposed to water and oxygen slowly at room temperature, speeds up when the catalyst is added, produces a noticeable amount of heat. Ooh, noticeable amount of heat. What does that mean? Exothermic. So what's the delta H? Negative. Okay. Exothermic is a negative delta H. So does that mean that the catalyzed reaction has a greater delta H? Anybody? No, no. Can I get a hand raise? Who said no? Okay, delta H does not change when a catalyst is added. It just said a noticeable amount of heat. So if you release heat really slowly, it may not be as noticeable because it warms up slowly. But as you catalyze the reaction occurs faster, therefore the heat's more noticeable because it's just being put out just a little at a higher rate. So that should explain that. Okay, another one? Yeah? 8. We did 12 yesterday. Okay, so in 8, you were given ozone goes to O2. The first step is ozone going to O2 plus a single oxygen. So this is the first step. If this is the overall, you just had to come up with not put a star on it because this is the answer here. You just had to come up with a way to, 1, get 2 ozones, so you definitely need a 2 or a secondary ozone here. You need to find a way to cancel out the O singlet as an intermediate, and then, what's that? 7? Okay, let me finish this. And then oxygen diatomic, you needed another one, so we just did that. Let me just leave that there for a second. Okay, I'll show you this one. Thank you. Okay. So on this one, you had a intermediate of the iodine singlet. You had another intermediate of the H2I. And then, since there were 2 I's, you can cancel out this one and this one, leaving you overall the full reaction being iodine diatomic plus hydrogen diatomic yielding 2 HIs. Okay, another one? 6. So you're given all the pictures. The pictures were what you were supposed to kind of utilize as the reactants and products. So in D it says, how many elementary processes does a mechanism have? Which one? Oh, E. Okay. So you have to look at the number of reactants. 1 second. You guys, give me a favor. Start multiple choice for a second. I just gave that to you. We'll start from the They're trying to keep it almost 23 for a couple minutes. What number are we on? 8-ish. Okay. While you guys are finishing up a little bit more of that, can you keep your Arrhenius or outline, whatever you took, what start like 3.5 pages and then keep doing your best on your Keep going. Take a couple of minutes. I'm almost done. The last one you're on, we're just going to put that in the back burner for a moment. All right, put your multiple choice away for a moment. Who's over halfway done? Okay, I was hoping you'd get about halfway. You didn't spend too much time on it, so we'll jump on the rest of that after we finish up Arrhenius notes today. I'm about to modify a couple things, and I'll tell you about our deadlines and so forth, especially in those labs. You're like, which lab is this? Making sure you're clear. All right, so the question I was asked before, sorry, I had to get some chemicals disposed of. I have mercury thermometers. Woo, you don't have those in class anymore. All right, so on E, specifically on the shape ones, it was just talked about like the molecularity of the reactions, each elementary step. So you have 2 reactants, it's a bimolecular step, it's 1 reactant, it's unimolecular, if it's 3 reactants, then it's a termolecular. So that's, in this case, according to the shapes, you had 2, 1, and 2. Okay, any more on mechanisms right now? Yeah. 4. On 3, it's 3 elementary processes. On the way on this one now, this if I've modified it since this key was scanned, that's why here. There's only 3 steps, so it's 3 elementary processes. All right, keep going up. So we kind of went from the bottom up. I think you guys, these are all definitional based. You guys are probably okay on the rest of those. Are we okay? Okay. So let's look at Arrhenius a little bit more. You guys did a good job. Basically, you have another equation. There's one more relationship we're going to learn with activation energy. Before we talk about the equation, though, I want you to graph this. So this has a relationship to activation energy, but I want you to be able to do it graphically. So I'm going to read this to you, write down the details you need, and let's see what you get. Okay. So biological mechanisms, reactions, nearly always occur in the presence of enzymes, such as which are catalysts. The enzyme catalase, right? We talked about catalase yesterday. Acts on the decomposition of hydrogen peroxide and reduces the EA. What's EA stand for? Activation energy. From 72 kilojoules per mole, which is the uncatalyzed version, to 28 kilojoules per mole, which is the catalyzed version. The total change in energy for the reaction is negative 204 kilojoules per mole. Write the balanced chemical equation and then draw the reaction coordinate, aka the potential energy diagram for this reaction. The whole packet. This is like Arrhenius example 5, but you didn't have to. you guys need to put your laptops up, go ahead and do that because I know that you don't have a lot of space on your desk. Shouldn't take too terribly long. Your reaction 2:1 ratio, 2 waters at the end there. And then in terms of the potential energy diagram, you should have just one, pretending it's one elementary step, so one pump. But overall it's NO or XO. XO, so you could have labeled numbers on the side of the potential energy diagram. It doesn't really matter where you start and where you end as long as the changes are as they indicated here. But overall, I kind of just drew a little arrow to say between the energy of the reactants and the energy of the products, that was a negative 204 kilojoules per mole, so I labeled that delta H for us. It was labeled delta E up here, but that is related to delta H because it's the energy exchange within the system. And then the blue hump is EA1, and it's just the energy from the reactants to the peak. That was 72 kilojoules per mole, which is how activation energy is denoted. It's the same as a lot of our other energies, kilojoules per mole. And then a catalyzed reaction has a lower activation energy. So I start at the same place, I end at the same place. It's just the middle region that's changing, and that's just got a lower activation energy of 28 kilojoules per mole. Does that make sense? Talk to me. Questions? So my graph is little, sorry. So it's the same as we did before. It's the energy difference between the reactants and the products. So I kind of just eyeballed where that point was here from the beginning of the reaction into the product. So this difference in energy is negative 204. So it's decreased in energy by 200 kilojoules per mole, which is representing our exothermic delta H. So yeah, that's one thing we need to be very clear on, is how to identify stuff from a reaction coordinate. EA is from reactants to peak, delta H is from reactants to products. Really, there's not anything else we really identify from that. Okay? All right, thumbs up. Okay, so based off your reading, I'm going to talk. Oh, actually, hold on. What's the activation energy uncatalyzed reverse reaction? So the uncatalyzed reverse reaction is going to be, it's going to be huge. Anybody? So how are you doing that, Quee? Okay, so the catalyzed piece here is 72 kilojoules, right? Okay, so what are you doing for the reverse reaction? So, okay. So you're going in the reverse, so you're going this way, right? So you have to count from all the way from the products, all the way tippy top to the peak, which is 204 plus the 72. So this is 204 plus 72 kilojoules per mole, which is 276 kilojoules per mole. So that's why the forward reaction is favored versus the reverse, because the forward is super easy to achieve 72 kilojoules, but the reverse ain't no way. It's going to be quite difficult to achieve that. Yeah. because it's still just the activation energy as a whole. It's just the net energy that's required to start that reverse process. Yeah, and activation energy will never, ever, ever be negative. Okay, yeah.
If it was a system that was having both forward and back, forward and reverse reaction at the same time, would there be activation energy that's
No, it would still be different. So if they were occurring at the same rate, then some particles have enough energy to do it in forward and reverse. Okay, so we'll talk about equilibrium more. Okay, and then of course I think you guys could do the catalyzed reverse. How would that? What would that number be for the catalyzed reverse reaction? So the 204 plus the little bit here. So that's 204 plus 28. Okay. All right. So quick. Oh, I just want to remind you at the very bottom of the Arrhenius reading, there was this nice flow map. And if you understand everything there, and you kind of recognize what each piece is talking about, that might be something good to go back and look at before your test Friday, okay? All right, so these are some reminders first. Some of these come directly from the reading. So if you want to annotate on that, or if you want to kind of like put a star on it in your reading, you can do that as well. Quick reminders, the collision model, the collision theory. We know that things have to have what two criteria to be an effective collision? Orientation and enough kinetic energy in the collision to meet activation energy. So don't just say have enough energy. We have to do a comparative, like say enough energy to meet activation energy. So we know that as you increase temperature, that does a really good thing for the rate of reaction, right? It's going to increase the frequency of collision and the energy of collision, which means that most of the collisions are likely to meet the required energy. But it doesn't have a linear relationship off the bat. So what was the rule of thumb? Increase the temperature by 10 degrees Celsius leads to a rate that's doubling, right? So the thing is, not every collision that's occurring within that system is creating a reaction. So there's two other factors we have to consider, activation energy and orientation. So basically, as temperature increases, the frequency of collisions increase. Those particles have more kinetic energy, so they're likely to meet EA. So this is a review right here. Therefore, the rate's going to increase because there's a greater number of collisions. But here's the observation. We don't always see the rate increase as much as we think it should. We know, like, the general rule of thumb is by 10 degrees, the rate's going to double, but we don't always see that. So what else do we have to consider? What was the kind of the theme of your reading? Arrhenius' equation. He didn't talk about correct orientations much. What kind of energy? Activation energy. Okay, so kinetic energy plays into that. So we still have to consider the activation energy and how does that really impact the rate of reaction. So some collisions are occurring, maybe with the correct orientation, but not correctly meeting their activation energy. Okay, so this was a graph you guys have seen before. This is the Maxwell-Boltzmann curve. We know that does the area under the curve change? Does that change the temperature? No, okay. So what you're seeing is that there's a designation here now of activation energy, which is the energy required for whatever this reaction is. So this is the activation energy required. The blue curve has very little fraction of particles that actually meets that required energy. The pink one has a greater number, and then the red one has a whole heck of a lot more, right? And so, of course, these extend on and on and on. So what you're definitely seeing is that at higher temperatures, remember these are all representing average velocity and aka temperature, you're seeing a greater number that are able to meet activation energy. But just because they need activation energy, does that mean they're going to react? No, because potentially they could what? Not what? Not have the correct orientation. This is quiet. Okay. I'm not going to do this piece. Doesn't matter. Okay. So draw two reaction coordinates for me. One endo and one exo. Do a quick sketch there. And what was the tip, the peak called originally when we were talking? Transition state. Okay, there's a transition state theory, and then there's a collision theory. The collision theory they're both explaining the same thing. It's about how reactions occur and, the energy required to make those reactions occur correctly. But they call the peaks two different things. So I just want to make sure you're clear on the two ways you can name the peak. So for exo, you're starting high, ending low. For endo, you're starting low and ending high. Okay. Who has a higher actually first, what are the axes? What's the y-axis? Potential energy, okay. So we can see over the course of a reaction, the molecules themselves are increasing in potential energy, and that's why they peak here. And you guys read about that as well. The kinetic energy is being transferred because energy is not lost. The kinetic energy of themselves, as they form closely together as a bond, they're increasing their potential energy. Potential energy is technically chemical energy. So as you meet this peak right here, that's also known as an activated complex. Same thing over here. Activated complex is just another theory which explains the transition state. We have a complex of molecules that are in such a weirdly organized way. They have really, really high potential energy. A lot of times high potential energy is not favorable because they're not very stable. So what they want to do is they want to fall down, in this case, to form products, because that's maybe in the most stable arrangement for those molecules now. So when they do form products, they go from here eventually to here. Overall, they're releasing a lot of energy. So that's our delta H again. Negative. That's our exothermic process. This was favorable back in thermodynamics, right? This was the preferred version because overall the reaction system is releasing energy. Okay, and then opposite, so we have our endothermic reaction. Our delta H is positive. This is less favorable. There's actually another reason now that we understand kinetics a little bit more. There's another reason about where the favorability explanation comes in. Which reaction is more easily achieved, exo or endo? Certainly, right? So exo because the activation energy 1 versus activation energy 2. Activation energy 1 is much what? Much lower, okay? Put a K there, put an E. Okay, so the activation energy of 1 is much lower, so it's much more easily achieved. That relates to the thermodynamics and the nature of the reaction. It also relates to the rate of the reaction. So despite knowing the delta H, does the delta H tell us anything about the rate of the reaction? No. The EA is going to tell us something about the rate of the reaction. Which of these occurs faster? The exo one, right? Because you're going to be able to hit that EA at a much higher rate than hit the EA2, which is of the endothermic reaction. Okay. So we're now connecting thermo just a little bit with kinetics, but we won't do much more than that. Thumbs up if I can move on. Thanks. Okay. So Arrhenius was starting to make observations about threshold energy, which now we have another name for it, activation energy. So he started to make a relationship between the number of particles that actually reacted, the temperature, and then the K value, which is the rate law constant K. So he started to make all these different correlations. Well, he started to realize that there was a linear relationship only when you thought about them in one way, or two variables were compared. So this kind of is the same thing we said earlier. He was trying to find a way to explain why the observational rate was not what they thought it was going to be. So they made these predictions, the rate wasn't what they thought it was going to be, so there must be a reason why. So he made some corrections to this weird equation we're going to see down here, which we call the Arrhenius equation, but he made some corrections to account for those differences in observations. So one thing was he tried to make a correction factor for the molecular orientation to say like, hey, even if they do meet activation energy, not all of them are going to correctly orient themselves in collision. So he tried to make a correction factor for that, and he tried to make a correction factor for not all the particles meeting activation energy. So that's kind of what his background is. Okay? Okay. So initially he came up with this weird equation. Okay? Do not even write that equation down. I just want to tell you a couple pieces about it, because we would never use anything like this because we're really fond of what kind of equations? Okay, easy equations. Fun fact, also linear equations, right? So we always like linear relationships because they give us a lot of predictability. They give us a slope to work with that could definitely represent something special, like in this case, activation energy. So his initial thought was K, right? Rate law constant K should be should be based on the temperature that these things are occurring. Because like we said, increased temperature, what happens to rate? Increases rate. But he kept seeing like kind of a not quite a predictable relationship between temperature and rate. So he made a corrected rate constant K by using all these other variables. So that's the corrected version based on the observation that they made. So he included activation energy. It says gas constant, but we are not going to use the atmospheric one. We're going to use the gas constant R, but that has what unit in it? Joules, right? So what's the R with? They're all called gas constants, even if it's energy. What is this R? 314 joules per mole K. Good. Okay, so we are speaking to energy, so we have to use the R constant with energy in it. And so he's still relating the K, the rate law constant, to temperature, but temperature must be in what unit here? Kelvin. Because the R has a Kelvin unit in as well. And then he tried to create these other variables, which we won't be using, but just to understand, he did try to relate it to the frequency of collision, which then also correlated to the orientation occurring. And then these are the fraction of collisions that occurred with the correct energy, because not all of them will. Okay, so we're not using this one, we're going to use the linearized version of this, which is this. Okay, this is the equation I want you to write down. In the reading it said, like, yeah, you don't have to memorize it. They stopped putting it on the reference tables when they changed the curriculum. I'm sorry. Okay, I do want you to know this equation. So pay attention to make sure you memorize at least the pieces that give you a graph and how you graphically analyze it. So no, did I do that? Yeah, I did. So I'll define the pieces that we really care about. We really care about the K, we really care about the T. We want to know how K, the rate constant, and temperature are correlated. Well, the initial way they thought about it, it wasn't a linear relationship. So when you natural log it, it is a linear relationship, which is why we'll have natural log of K. What is our slope? So negative EA over R. This is slope, okay? What is this technically? This is the y-axis, okay? What is 1 over t? This is the x, or the x, and this will also be the label of our x-axis. And this is just the y-intercept, right? We know that A is called a frequency factor. It's talking about like the number of times these collisions are occurring at that temperature. We're never ever given the A value, ever. Okay, we always graphically analyze this as a comparison between ln of K and 1 over t, but we just take this as we get it from the linreg stat plot. So we get this from the equation that calculator spits out for us. So what we really care about is the relationship between K and T, and eventually how activation energy relates to all of those. Okay, and then I think you guys got the rest of that. So yeah, we got all this. Yeah. This is a rearranged version of this. And that's solving, yeah, just for so it's basically taking, because the opposite of natural log is E, right? So that's our E to the negative EA over R, 1 over T. And so when you do the ln, or E to the natural log of A can come out, because ln's are multiplied together, so A comes out. But you will use this one because we'll use graphical analysis most of the time. We won't be using this quite as often. Okay, but we could interpret the relationship's directional proportionality here. Okay, so I want you to draw the graph of what the Arrhenius equation would look like. Sketch your graph. Start with the axes. So we are thinking about that linreg, the natural log K equals negative EAR 1 over T plus ln A. So now that you know the axes, think about how that graph would look and just sketch it. first one. 2, okay. 3, almost. Don't think too hard. It's a linear regression line, right? With a what kind of slope? Not positive, has. Okay, so it's just a straight negatively sloped line with axis y is what? L and K, and then x-axis 1/t, and t has to be in Kelvin. Okay, notice the difference here is that capital T is temperature, lowercase t when we're talking about integrated stuff is time. Okay, so yeah, L and K versus 1/temperature, negative line because it was a negative slope according to the relationship. So it was an inverse relationship. Not too hard. Okay, so then how would I take this information and solve for EA? So activation energy. Okay, so use the slope. So if I had if I plugged everything in like list 1, list 2, and then gotten my Lin-Reg equation, I would have the slope, right? Okay, so I would have a number. So what would I do with the slope to find this? Okay, so the slope is technically equal to negative EA over R, right? That's what we called M earlier in our equation. Okay, so then how do I solve for EA? Right, multiply by negative, what's the value for R? 8.314 joules per mole K. Good, because the slope is going to have temperature in it, right? So that's because that's the nature of the x-axis. So then the kelvins are going to cancel out, and this should equal EA in what units? Joules per mole. Okey-dokey. So if you're ever given a question that relates to like finding the activation energy, and you're given data that you can plug in a calculator, run your Lin-Reg as L and K versus 1/temperature, take your slope, multiply by negative R, that's your activation energy. Okay? All right, so, oh, sorry, I had a couple more points here. All right, so before, you guys have your kind of your sketch. I'll scroll back up, but I have some questions I want you guys to discuss first. So take 3 minutes, answer those last 3 questions because we already just talked about the first one.
It's not clear. It's a linear line. I feel like it takes my LDF very fast, but it doesn't change like how much you need.
But that's not in our equation. Think about what our equation has. It's a vert. We can't find one of that. All right, come back to me. 3, 2, 1. All right, so tell me, what do we know about activation energy at different temperatures? Hold up. So, I can't scroll up. Okay. On our graphs, our reaction coordinate graphs, we've never really graphed them at different temperatures. I mean, I just haven't, okay? But what you should be able to tell from this graph is that, I think JT said something related to this. Can you help me out here?
I said that the activation never change because it's linear, so the slope doesn't change either, and only multiplying by negative for
Okay, so noticing how we have it graphed at different temperatures. I know it's 1/temperature, but we're still graphing it at different temperatures, right? So at all of these temperatures, the slope is constant. So the way that this delivers information to you, you should see that the EA or activation energy is not changing at different temperatures. But there is something that's changing, okay? So there should be, on the graph that's in the packet, I think they graphed it as, how did they graph it? Activation energy versus, oh, I can't remember. Activation energy versus something else. But the activation energy should be constant because we know that the temperature affects the rate of the reaction, but not technically activation energy. So what does changing temperature actually affect? The what? The K value, right? So what's the K value going to do? As you increase temperature, what happens to K? So increasing K, what does that mean technically about the speed of that reaction? It's faster, right? And that definitely makes sense because we've talked about how faster reactions are due to the increased kinetic energy these particles contain. Okay, so a larger K value means the reaction is occurring faster. And then this is just a thought. We generally will graph these at different temperatures over time. All right, so let's do some questions with this. Before I do questions with this I think is like the major point you should really pull from anything related to Arrhenius. Yes, the equation. Yes, the graph. But this is the major point. Okay, so who gets large kinetic energy? Large activation energy. Does that mean the reaction's happening easily or not so easily? Not so easily. So is it going to happen fast or slow? Slow. Okay, so what should the K value correlate with? Or be correlated how? It should be smaller, right? So these are the major points, really. And then as you think about how that impacts the graph, larger activation energy, how does that impact the graph? Say again? Well, it's a large activation energy, right? So like this slope versus this slope. Which of those would show a larger activation energy? The red one or the black one? The black one, so it should be more steep. Okay? Because the R constant's not changing, it's just the activation energy. And then the way you know, and this is kind of like the key point as well, the way you know you're going to have to use the Arrhenius equation is if you're given K values and temperature, but not like concentrations necessarily, not time. Okay, so that's how you know you're finding, not time, temperature. Let's supposed to say temperature. Yeah, see that, right? It says temperature. Question?
The steeper it is, the higher the activation is?
Mm-hmm. Which means the slower the rate of the reaction. All right, so if you have your packet, you can use those. Oh, actually, no, I printed out, I called it AP Chemistry, Kinetics, and Arrhenius Equation Practice, Arrhenius 1 and 6. Okay, so we're going to get to that in just a minute. So looking at this data, you guys have your calculators? Have your calculators. Almost certain. Alright, so we see this reaction, we don't really care, but we know that this data was collected at several temperatures, and from those several temperatures, they found a K constant, so they found the rate law constant. I want you guys to put this in your L1 and L2, or whatever you call them, C1, C2. And what are you plugging in for your, you guys usually do your L1 and your X? Yeah. Okay, what are you guys plugging into your X? 1 over temperature, but how do I modify this temperature? It's converted to Kelvin. I cannot plug this straight in the calculator, okay? This has to be 1 over temperature in Kelvin. So you're plugging this as in 1 over what? What's 273 plus 15? 288, thank you. And this is 1 over 298, and this is 1 over 308 Kelvin, and this is 1 over 18. And all those are in Kelvin, but your units in the calculator don't matter. All right, so that's our x-axis. What are you plugging in for your y-axis? Say again? ln of the K value, right? So ln of K. So we're just going to natural log all those values, which I think you can do at the top of your list, but regardless. So we want to know the linearity between these these two variables. We want to know the relationship. So now what are you running after you plug this into your scat plot? You're doing what? Okay, so we're writing this. We're getting our y is equal to mx plus b. And what is that when you guys get there? Maybe compare with your partner just before you start. partner, what's your lin reg? Negative 5,638. Oh, 5,638.34 x plus 16.62. Okay, thumbs up if you got that. Pop a brother out if you did not get that, because you guys are the calculator savvy folks. What's the r squared value? 0.99. Right, I don't know why Concord Middle School is calling me. Anyway, so this is r squared, that's very linear, okay? Now, you guys find EA, activation energy, from that data.
It's like the slope, like the
Okay, so the slope is negative EA over R, that's equivalent. So how are you solving for EA? Taking the slope, multiplying by negative R. We all know what R is. Don't just put R in paper, write the value out. So you're doing negative 5,638.34 times negative 8.314 joules per mole K. The slope is technically it's 1 over T. So it should have a temperature, Kelvin unit in the top someplace. Okay, so the K's cancel out, we get joules per mole, and that value is 4.687 times 10 to the what? 4th joules per mole. Okay, so now that's just kind of a ridiculous number to write like that. What is that in kilojoules? 46.87 kilojoules per mole, yeah. So a pretty large amount of energy, but you know, we don't really know what we're comparing to, so we just have to call it a day, okay? So we can now plug into calculator, we can find ln, or natural log, linear regression. We can find the slope, from the slope we can derive our own activation energy. Yes? Okay, and then I have a series of questions on the packet. What is that next to you in the packet? It's on the lower left-hand corner on the page that starts with what? More kinetics practice. It's down there. I did not kill any trees this time. Okay, I'm not going to go over the comparative K's, but what we can do if we're given no values to find our own our own linear regression, we could take a variety of temperature values and K values and solve for our own EA activation energy, not given data points to plug into our calculator. You could technically do that, but we're not going to do that right now. Okay, so let's work through this part together, okay? So we have a reaction, experimental values for nitrogen monoxide plus ozone yields nitrogen dioxide plus oxygen. We have a set series of temperature values. We have a series of little k rate law constant values, okay? Is this reaction fast or slow? Justify your answer. Talk to your partner in 30 seconds. That's all the data you have.
So it's a smaller the K, the lower the slope. So these look like
All right, back to me. 3, 2, 1. Drew, help me out.
It's fast
Why?
because it has a really big K value.
Look at these. Like, these are in the billions, right? Very large K values. That's the only data you have, right? You have to look at that. So the temperature doesn't really help you a whole lot, but looking at the K values certainly do. Relatively, are these high or low temperatures? What is it, Cassie? Pretty dang low. What is that technically in Celsius? Some negative Celsius value. Those are low values, right? So what you would kind of need to connect is that the K values are large at a relatively low temperature, which means it's a fast reaction. That's kind of what you're connecting those variables wise, but overall, yes, K values are quite large, which large K values mean fast reaction. Okay, and then talk to your partner, what's the overall order? Remember, that's the only data you have in front of you. Now, mine might be easier to see than yours. You guys can see that. Don't get crazy on me. It's temperature data, it's not concentration data.
Yeah.
What'd you say?
Same thing.
That's under elementary processes, which it doesn't tell you this is an overall reaction. Right. I want somebody to raise their hand if they are confident in themselves and what's happening. I got two. Chase, what do you think? What do you think?
Second order.
Why?
In the chart it says K is liter per mole per second, essentially equals like 1 over concentration.
Beautiful. That's the only data you have to look at. Do not graph anything. Do not try to make correlations between K and temperature. You don't know how to do that unless you're graphing. That's Arrhenius equation. So you look at the data, and the K value is telling you 1 over molar per second, which, one second, remember the rate itself, rate law itself is K concentration, right? So the only way I'm going to get rate to be correct, which is molar per second, this value, unit-wise, has to cancel out the molarity. Well, the molarity, in this way, it's going to be first order. But if I graph it, or if I write it the way it's written here, which is molar per second, I need to cancel out one molarity, so I have to have 2 molarities to cancel this out to leave me with molar per second. So yeah, second order. Because K units. Question? Question? The BCE is an overall reaction. You cannot use that at all for coefficients. Yes, so the only way you can use the balanced chemical equation if you have individual elementary steps and you know which elementary step is the rate law, rate determining step, that's the only time you can pull coefficients, so never, ever, ever any other time. Yeah.
Wait, there's going to be a dumb question, but since that's for second order, what would that look like if it was first order? Like, how would we know if it was first order? What would it say for?
So if it were first order, you'd only have molar, not molar squared, right? Because this would be to the first order. So then the K would have to be 1 over time.
So it'd just be liters over seconds?
It would just be over seconds, or seconds to -1. You wouldn't have liters or moles. The reason they put liters and moles is because they want you to know that this liters per mole is actually saying the same thing as dividing by molarity. So liters wouldn't be involved at all in K. It would just be 1 over seconds. Okay? All right, so continue. What is the activation energy? Now this is y'all, okay? Find the activation energy. Compared to the person next to you, the next big there. All right, does anybody have a y or a linear regression equation? Y is equal to 30. I got 1433. 35. I remember now. I probably was wrong here. Point what? Okay, so this is our linear regression line. Give me a thumbs up if you got that far. Okay, and then you guys have, yeah.
Let's see, the values are given.
The value, the
Units.
units for which one?
For slope.
For slope. So it's activation energy over, negative activation energy over R, right? But it's a relationship between 1 over temperature and ln of K. Okay, the K values, K units change every time because it depends on the type of reaction or order it is. So we regard it as temperature, right? So Kelvin. So this is technically just Kelvin, and when you take EA for negative R, the R has Kelvin in the denominator, so it cancels Kelvin out to leave your activation energy as joules per mole. It'll always be joules per mole until you change it to kilojoules. Okay. All right. So go ahead, guys. What is that? What is EA? Okay. So you're taking the negative 1435.71 times negative 8.314 joules per mole K. I'll put Kelvin right there, and then that will be 11.9. I heard kilojoules, right? But originally you got like 11.936 joules per mole. So we rounded. Okay, so I went to kilojoules because usually if you have a large number over 1,000, you're probably going to get kilojoules. Yeah. Sometimes it's difficult. Look at your data. So looking back at your data, I think everything was to 3. So we recorded them all to 3. Okay. All right. So go ahead and now find the K value. Oh, sorry. Before I move on from there, is that a relatively high or low activation energy? Relatively. Think of it. The last one we did was like 43 or something like that kilojoules per mole. And the first example we did today when we graphed it, it was like 72 kilojoules per mole and then like 28 catalyzed. So this is what? Relatively low. Okay. So if it's relatively low, what should that mean about your reaction? Okay, it's fast. And did we already determine it was fast? Yes, the K values were large. So all of these things are correlating now. So you should be like, yeah, pat myself in the back because I know I'm in the right place. All right, now find the K value at 455 Kelvin. Before you find it, I want you to predict it. Predict it using the data, right? So think about where these data points are. You're looking at 455. 455? All right, so you're predicting and now you're calculating. All right, that prediction doesn't take very long.
So it's about 9 degree change. No, that's so take 3.5, 3.5.
Yay.
That's pretty low.
You guys could graph it. I'm going to calculate it with my equation. What'd you get? My equation's a hair different from y'all's because I must plug the number in differently, so mine's a little lower than that, but it's still high.
I'm good. Actually, do more than
Alright, so some of you guys are graphing and just tracing to find the K value. If you're doing it by plugging into your equation and you find your LN, does anybody have that for me? Yeah.
Oh, for my LMK, I got
Okay, so when you plug in your EA, negative EA, remember this is the joules version. Joules version because the R value is in joules. Joules per mole. Cancel, the Kelvin comes up to the top. That's how we've been talking about slope anyways, Kelvin. Kelvin cancels with the 1/455 Kelvin. Blah, blah, blah. Okay, so who got approximately this? Okay, I did too, thank you. And how do you offset, or how do you negate ln? E. Okay, so K is equal to
6.6 times
10 to the 10th per time. Thank you. All right, so this is what I got when I mathematically calculated. The graphing people, how close were we? We spot on? Okay, yeah. Good question.
If we do graph on the how do we show?
It's hard. That's why I think you should be showing work like this. Especially because a lot of times they'll say, like, utilizing your data from above or utilizing your answer from B, find the data from this. They want you to use the activation energy you just found, plug it in, and they want to see your processing of that. So that's what they'll try to guide you to say, show your work. Yeah.
So if you don't remember this in the equation, you plug your numbers in.
Hypothetical. Some you get points someplace, but probably not throughout. Okay, but you would not have to calculate this on the free response. Okay, you have to know the relationships for multiple choice. You would not have to literally calculate it on a free response. What you might have to do is talk about if you were to calculate, how would you process it? So if you were to calculate the EA without out actually calculating, what would you have to do? Given data. First step. Plug in what in your calculator. That's not specific. Whenever temperature in Kelvin, okay, then natural log of K and Y, then ln reg, and then get the slope. So you couldn't just say negative R, you'd have to say multiply the slope by, okay, and that would be your EA, okay? Okay, so if you can say it out loud, like you can technically calculate, okay? So I'm going to hold off. I won't do this one. I might do it tomorrow. So I've tried to make some time in class for us to practice some more. Let's take let's take a couple more minutes on multiple choice, okay? So go back to that. We'll go through some. You still have your laptop? Go put that laptop up for me. And then I'll tell you guys our weekly plans here. All right, so I got 2 minutes left with you. Here we go. Ready? Come back to me real fast. Homework. Finish multiple choice. Who's close-ish to done? Okay, this is a safe fail practice. Okay, so we will check multiple choice first thing tomorrow. We will also be starting free response tonight. What I want from you is to start number 1, 2, and 5. If you don't finish the whole entire thing, it's fine. We'll have some time in class tomorrow. I'm scratching a lab because I hear there's some events happening Thursday night, so I can't switch days because our test, like I have a pretty strict deadline like David did, but I can't allow for my time class to practice and like face run with you. So I want you to start 1, 2, and 5. I'm gonna have you guys present FRQs and I'll help you out. So number off for me, starting here, Jillian. Just so we're just going 1 through 7, okay? You're helping present 1. Go. 1.
2, 3,
4.
You better write down your numbers, people, right?
3, 4,
5,
7,
2,
5,
6.
2,
Yes, okay, so those are, tomorrow you guys will regroup, but in class tomorrow we'll be checking multiple choice. We will be finishing free response in class, and hopefully we'll check all the free response in class, okay? So we're going to try to knock all those out, but the best thing for you to do is come in with partially 1, 2, and 5 done tonight, and like maybe there's no more time to finish up the others so that we can present them tomorrow in class, okay? A couple people ask me if stuff's on paper, like lab stuff's on paper, it's fine. Who's gives labs kind of all the way through on paper? Delta, Delta H, Delta S, Delta G, we added baking soda.
It was like one
It was one sheet of paper.
It was this one.
Yeah, I know. Okay. That's fine on paper, totally fine. All screwed up is, if you got like 75 to 90% of that done, I'm fine with that. I just like to kind of
No,
split
that
those
was
off.
the one.
Your age grade, you know.
It was on his paper. Like, we can we can type it up.
Come for the
If you guys need to come for intervention, as long as your teachers don't care, you need to care.